Hello everyone, we will discuss problem painting the walls of weekly contest 350. So the problem statement says that you have a set of walls, n walls, and you want to paint all of these walls. And you have two types of painters, a paid painter and a free painter. So the paid painter will, to paint each wall, it will take the cost associated with that wall. And the free painter takes zero cost to paint a particular wall and 1 unit of time, but it can only work when the paid painter is working, so it cannot work separately. So that means suppose that you choose this particular wall and you assign it to the paid painter. Okay, so it will take you 2 units to cost, and since the paid painter takes 3 units of time, that means the free painter can paint some three other walls for free. Okay, so he can paint these three walls, and that means in cost 2 you would have painted all of the four walls. But suppose if you had taken something like perhaps this wall, and you're assigned this to the first paint, like the paid painter. So for 2, and that's the only wall you assign it to the paid painter. So that means you have 1 unit of free time, in which 1 unit of time in which the free painter can work. The free painter can only paint one additional wall, maybe this wall or this wall or this wall, but uh, you won't be able to paint all the walls if you assign it this wall only to the paid painter. So the question asks, what is the minimum cost to paint all of the walls? Okay. So I will first explain an n-cube solution that I tried, and then how I converted that to an n-square solution. So suppose that uh, you are going from the 0th wall to the n-1th wall, and you are here at some ith wall. Each wall has for each wall you have basically two decisions that you can take. Either you take the wall, that means you assign the wall to the paid painter, or you don't take it. That means later on, like, it will be painted by the free painter. Okay, so I am here at the ith wall, and for the previous walls from 0 to i-1, I have taken, for each of these walls I have taken the decision 1 or decision 2. Okay, so what information do I need from this previous segment, from the segment of 0 to i-1? You need to know, number one, for all the paid walls, that means the walls which were assigned to the paid painter, what is their total time? Their total time. Why? Because suppose the total time here is 10. That means that you could, paint 10 free walls. Like if uh, from I to n-1 there are only 10 walls remaining, and from here you had taken some paid walls, and the total time, the summation of time was equal to 10. That means you don't really need to pick anything. Like all these walls, you don't need to pay for them, because the free painter has this 10 units of time, and he can use that to paint it. Second is, you also need to know, in this previous segment from 0 to i-1, how many unpaid walls were there, because those walls also need to be painted by the free painter. So how many unpaid walls were there? When you are at the when I equals to n, that means suppose you are at the like you have painted you have decided for all the walls from 0 to n-1, and now you're at the nth index, indicating that you have taken the decision for all the other walls. So in that case, you just need to check that the total paid time should be greater than equal to the unpaid walls. That means from the 0 to n-1 segment, you had taken some paid walls, and these paid walls had some time, capital T. So the total number of unpaid walls, since each unpaid, like free painter will paint one wall in 1 unit of time. So the number of unpaid walls should be less than equal to capital T, because this is how much that how this is the total time for which the free painter can work for. Okay. So if you look at the constraints, so the constraints on uh, n is 500, and this can also go like this can also go till 500, and the total time, you also don't want the total time to be greater than 500, because like you don't want the total time to be greater than n, because in that case like you can just um, paint all the remaining walls for free. So what I'm trying to say is that if you want to represent this in a dynamic programming solution, so you would represent it using you can do it using a three-dimensional vector of size n cross n cross n. Okay. The transitions will look something like this. dpijk means that you are at the ith index, you are making a decision for it. J will indicate, let's say, the total time from the segment 0 to I minus 1, the total paid time for the paid walls. And K will represents the unpaid walls, sorry, let's call them free walls, in the region 0 to I minus 1. Now from here on, you have two choices. The first choice is you you do not pay for this particular wall. So what will then happen is you will go to the I minus 1, you want to make a decision for the next index. The total paid time will not change, and k will increase to k plus 1. The second possibility is that you pay for the current wall, and in that case your total paid time will exceed, like go to time of I, and then the unpaid walls will not change. Okay. One thing to note here is that if j plus time of I, right, or if this value is greater than n, okay, then you don't really need to go further. What I mean by that is, because if you have more than n free time, suppose your n is 20, that means you have 20 walls, and your free time is greater than 20, then obviously the free painter can paint all the remaining walls, because you have more than you have um, you have at most n walls that you want to paint, and you have greater than n time. So this value doesn't really need to exceed n. That's why the dp will be constrained. Like otherwise, otherwise this time of I value, like the total time can be very large, but you don't really want it to exceed n. So this is an n cross n sort of dp, and this is what I did first, but it will give you a TLE. Now, how do you go from this solution to an n square solution? Well, for that you need to understand the base case. The base case is when I is equal to n. That means you have, um, you know, solved. You have for all the walls you have made a decision. So what do you do in that case? Like I said, in that case you just compare j. J is the time that you have. That time should be greater than or equal to k. Correct? Or what you can say is that j minus k should be greater than equal to 0. So instead of storing j and k separately, we are only concerned with their difference. So we can store, like instead of these three things, we can just store the index and j minus k. Like j minus k indicates the difference between uh, the total paid time that you have, and the total number of unpaid walls that you had. So effectively what it means is how many extra free walls can you paint from this point onward. So suppose you're at this ith index, and previously j was equals to 20 and k was equals to 10. That means in this segment the paid time was 20 and 10 unpaid walls were um, there. So these unpaid walls, they need to be painted at the end, right? So minus 10 will definitely happen from the final time. So effectively you have 20 minus 10 free time remaining, because these 10 walls will obviously utilize the paid time. So you have effectively 10 free time remaining. That means you can paint 10 extra walls without compromising, like assuming that you have painted all the walls before yourself. So that's why, since you're only concerned with, at the end you're only concerned with j minus k, you just need to store j minus k in your uh, dp state. Now how will the transitions here look like? They're again very, like, you should try to write them on your own, but let's call this term um, delta. Okay, let's call this term delta. This is the difference. So if you're standing at the ith index and delta is your difference between the paid and the paid time and the free walls, so there are again two cases possible. Number one, you don't take this wall. So in that case, your transition will be dp of I plus 1. And since you're not taking this wall, you're just compare it with this, right? You're not taking the wall, like you're not paying for the wall. So your k is increasing, your unpaid walls are increasing. So what will happen to your difference? J minus k. Previously difference was j minus k. Now the difference will be j minus k plus 1, which will be j minus k minus 1. So your difference will decrease by minus 1. So it will go to delta minus 1. Otherwise, you choose to take this wall. So in that case, uh, your total cost will be cost of I plus, also in this transition, uh, cost of I will be added because you are taking the ith wall. And what will happen to your delta? Your delta will increase, like your effective free time will increase by time of I. Okay, like here also you can see that j minus k is going to increase, so since j is increasing by time of I. And then what will be your condition? What will be your end condition? Your end condition will simply be, if I is equals to n, then this delta should be like greater than equal to 0. Okay, that's how you will solve it. Now two important things here. You are storing the difference, right? But the difference is not necessarily going to be positive. It can be negative as well. So what is the range of this j minus k? What is the range of this j minus k? So let's assume that we do not pay for any wall. We do not pay for any wall. So in this case, in that case, j will be 0 and k will be uh, n. We are not paying for any wall. So it can go till minus of n, j minus k. And what will be its upper limit? So upper limit can be very large actually. But like I told you somewhere here, um, yeah. So like I told you that j cannot exceed n. We discussed that, right? Uh, yeah, j cannot exceed n because so j cannot exceed n. J will be less than equal to n. So because of that, j minus k will be bounded. J minus k will also be less than equal to n. Because why j cannot be greater than n? Because if you have more than n free time, so in that case you can just stop, because uh, you have more free time than you have the number of walls, right? So this will be the limit of j, the difference j minus k. And the dp table, like, it cannot take negative indices. So one way to construct a dp table like this is, either you can use a map, but instead of using a map, what you can do is you can change its range. So you can map minus n to n to some positive range. So what you can do is, suppose I add n to this and I add n to this. So the new range becomes 0 to 2n. So effectively we can use 0 to 2n as our new range, and suppose suppose I have some dpij. To find the actual true time, I will subtract j by n. So um, suppose my delta was equal to the difference between j and k. Suppose it was equal to n minus 1, right? So instead of using delta is equal to n minus 1, I will add n to this, and my new delta will be 2n minus 1. This is only for the sake of convert, so that like this range is converted from negative to like complete positive, so that it can be represented in your DP. And yeah, that's how you will solve it. If you can either solve it using recursion, or you can solve it iteratively. I solved it iteratively, and I will um, discuss that approach now. So I made a DP array of size n, and uh, into 2n. So n is the index I'm at, and this actually represents the difference. So j here represents the difference between the paid time and the free time. Paid time and the number of calls that are unpaid. Okay, and then I'm just filling this DP table. So since DP of ij depends, since DP of ij depends on DP of I plus 1 and something else, so I can just fill the DP table in reverse. So the base condition I took here was if I was at I equals to n minus 1. If you're writing it recursively, you can take the base condition as when I equals to n. And at this point, I just check if the real time is converted by subtracting n from j. So if the real actual time or the real actual difference, so this is the actual difference, and this is actually the mapped difference range. So from minus n to n, I add 2n to it and I convert it to 0 to 2n. So that's why this is actually from 0 to 2n. So I find the actual difference, and if I am at the last element and the actual difference is greater than equal to 1, so that will mean that I can take the last element. Like the actual difference, what did it mean? It meant that how many extra unpaid walls can you take from this point onwards. So I can take this wall, there is no point paying for it. Otherwise, if the real time is like less than equal to 0, then I will check that by taking this current wall, by taking this last wall, by paying for it, if the new real time, so the new real time will be the old real time. Uh, the real time just means the difference plus whatever um, time you contribute. That should be greater than equal to 0. If that is okay, then I will take this wall. And if that also doesn't work, so suppose the actual difference is it's like the actual difference is minus 10 and your time is 5. That means you can just add 5 to the difference at max. So the difference will still be negative. Uh, so that means there will be still some walls which you could not paint, which the free painter could not paint. So in that case, we will define dp of ij as int max. That means it's an invalid state. And then these are the two transitions I talked of. So either you do not take the current um, wall, either you don't pay for it. So in that case, your transition will look like your difference will reduce by -1. And I added a check here that j should not be equal to 0. because in that case j minus 1 will be -1, and that's not, like, that state will never be reached, because the the maximum, like the lowest value of difference is -n, and since j is equals to -n plus n, like we are mapping it, so j's minimum value can be 0 only. So j's minimum value can be 0 only. It cannot go less than 0. Otherwise, I will like I will also check that either I can do this or I can take myself. So if I like take myself, then the new cost will be the cost, and the difference will increase by my time. And like I said that there is a cap, there's an upper cap on this, like this is the range from -n to n. So I take a cap on the difference, so the difference cannot exceed 2n, because the mapped range is from 0 to 2n. So the difference cannot exceed this value. So I take the minimum of 2n and the new difference, and then I take a minimum of that. That's how you can solve it iteratively. I'm sure the recursive code will be a bit simpler, so you should try to code it on your own. Just to summarize the solution, we need to know the index we are on. We need to know the index, and we also need to know the difference between the paid time and the unpaid walls before us, like before the ith index. And that difference needs to be greater than equal to 0 at the very end. So at the very end, when I equals to n, that difference needs to be greater than equal to 0. And then when we are making a transition, when we are going from the ith state to the I plus 1th state, then we have two choices: either we take it or we don't take it, and based on that the difference will change. I also discussed that the size of the dp table will be n into 2n plus 1. So, and the reason for that is the actual difference lies in -n to n. And since we cannot represent negative indices in, like in simple arrays, we will convert that to a new mapped range from 0 to 2n by adding n to both of these from the left. Like we're just simply shifting the range. And that's why the size of the DP table is something like this. That's all for this video. Thank you for watching. Bye bye.